14,000 years ago, the Earth was emerging from the grip of the last ice age. Temperatures were rising, glaciers were retreating, and greenhouse gases like carbon dioxide were climbing in the atmosphere. But then, something unusual happened in the southern hemisphere. The warming slowed, and for nearly 2,000 years the climate tipped into a cool phase called the Antarctic Cold Reversal. For decades, scientists wondered what could have caused this pause in warming. Now, new research from the Alfred Wegener Institute has uncovered a surprising player in the story: tiny Antarctic algae called Phaeocystis. These organisms are invisible to the naked eye, yet their influence on the planet's climate was enormous. During long Antarctic winters, sea ice spread far out into the Southern Ocean. When spring arrived, the ice melted back, releasing a flood of cold, fresh water into the sea. This meltwater created a thin, nutrient-rich surface layer bathed in sunlight, the perfect breeding ground for massive blooms of Phaeocystis. These blooms covered vast stretches of the ocean and pulled enormous amounts of carbon dioxide out of the atmosphere. The algae not only absorbed carbon through photosynthesis, but also packed it into sticky clumps that sank into the deep ocean, locking away that carbon for centuries or longer. In effect, these microscopic organisms acted as a planetary brake, slowing down the rise of greenhouse gases and reshaping the climate trajectory of the time. For years, this story remained hidden. Unlike diatoms and other plankton, Phaeocystis leaves behind almost no fossils. Traditional geological methods, which rely on hard shells or chemical signatures, couldn't see them. They were ghosts in the climate record. That changed when scientists began using a new technique called sedimentary ancient DNA, or cetDNA. By sequencing genetic fragments preserved in deep-sea sediments, researchers could finally reconstruct which organisms had thrived in past oceans. In a sediment core nearly 2,000 meters deep in the Bransfield Strait, north of the Antarctic Peninsula, they discovered unmistakable DNA traces of Phaeocystis. The core revealed that during the Antarctic Cold Reversal, these algae had dominated the ecosystem, only to collapse abruptly when the planet warmed again. For the first time, scientists could connect Phaeocystis blooms directly to a period of large-scale carbon drawdown. The impact of these algae went far beyond the chemistry of the ocean. Their blooms reshaped food webs, feeding some creatures while crowding out others, and redistributed nutrients across the Southern Ocean. They even influenced the atmosphere in ways we are only beginning to understand. Phaeocystis produces a gas called dimethyl sulfide, or DMS. When released into the air, this gas helps form tiny particles that seed clouds. More clouds reflect more sunlight, cooling the Earth. In this way, the algae may have acted as a double agent in climate regulation, both pulling carbon out of the air and brightening the planet's cloud cover. But the story has a darker side when we look at today. The Antarctic environment that once fueled these massive blooms is rapidly changing. Sea ice, which provides the seasonal rhythm that Phaeocystis depends on, is shrinking at alarming rates. In 2025, Antarctic sea ice tied for the second lowest minimum ever recorded, part of a troubling trend of decline. Without the long winters of expanding ice and the spring melt that follows, the algae may lose their foothold. If Phaeocystis declines, less carbon will be transported into the deep ocean. Other algae, like diatoms, may take their place, but they do not store carbon as efficiently, and the structure of the food web could shift dramatically. The loss of Phaeocystis would not only destabilize ecosystems, it could also reduce the planet's natural ability to regulate its climate. The findings are a reminder of how sensitive Earth's systems are to subtle biological processes. We often think of climate change as being driven by large-scale forces: burning fossil fuels, melting ice sheets, shifting ocean currents. But this story shows that microscopic organisms living invisibly in the ocean can exert planetary-scale influence. By studying ancient DNA, scientists have opened a window into this hidden past, revealing how life and climate have always been intertwined. What makes this discovery so powerful is that it also reshapes how we look forward. If Phaeocystis could help slow warming thousands of years ago, what happens if we lose it now? Will the Southern Ocean's ability to absorb carbon weaken even further? Will cloud formation decline, amplifying warming? These are not abstract questions. They point to feedbacks that could determine how fast climate change accelerates in the coming decades. This research is not only about reconstructing history, it's about sharpening our forecasts for the future. By combining genetic tools with traditional geological methods, scientists can now build a much clearer picture of how ecosystems respond to change. The lesson is simple but profound. The stability of our climate depends not only on ice and air, but also on the fragile, unseen life in the ocean. If we ignore it, we risk underestimating the speed and severity of the changes ahead. The story of Phaeocystis is a reminder that even the smallest organisms can hold the balance of the planet in their grasp. Once, they helped cool a warming world. Today, their survival is under threat, and with them perhaps so is one of Earth's hidden defenses against runaway climate change.